Okay, one more track.
I got this from KUKA-TV.
Put that on YouTube or Twitter.
Inside my Storrs supplies. Bring them up to
I don't know if this mic is working. Is it all set? Good. At any rate, just what you said. I started out in the infantry actually during the war. When the war ended, of course, all of the high point guys that were in the Signal Corps and the long-suffering Air Force and so forth, they all got sent home, but I was just a young 18-year-old at that point. So then they discovered I was a radio ham. It was on my MOS, my military occupational specialty. So then I got shifted into the Army Signal Corps, ended up in Austria, basically monitoring the Russians and seeing what we could learn. And I was running the radio repair part of the unit, and I did a little bit of ham operations on the side. So that was really nice after the war. Anyway, when Dave first approached me on this, I warned him that talking on this subject really wouldn't have very much to do with ham radio. But since the techniques do bear some similarity, big antennas, reflections off the moon, coherent processing and so forth, we figured maybe it would work. So that's the situation. At any rate, the first thing you have to do if you want to do some radar mapping is to secure yourself an echo. Like the old recipes used to say, secure a sheep or something. And let's see, does this? It doesn't seem to be advancing, so could you hit the little space bar there? Yeah. Just press it now? It wasn't doing it then. Anyway, this is a diagram that I used before on the moon-bound stuff, but it's perfectly applicable here. It shows you starting out transmitting, and of course, as that power goes out, it spreads out, covering an ever larger sphere as the distance r increases. And by the time you reach your target, that power has been diluted by a factor of 1/4 pi r squared, which is the area of the sphere out there per unit area. So this is the flux reaching the target. We then define the reflection of that flux by an area given by the radar cross-section, which is a very complex quantity, and I won't get into that in detail, but it's basically related to the reflectivity of the surface times the disk, the area that's biting out the incident energy. And that's reflected, can you go back one just for a moment? That's then reflected, travels back to the receiving antenna, which is often the same antenna, and then that area bites out a fraction of the flux that's coming back, and that then gives you the power PR. The ratio between the transmitted power and the received power, PR over PT, is called the path loss, and that's what's been lost in the process of traveling out to the target and coming back. Now, just for convenience in deriving a quantity, you know, I think I'm going to sit down here. I've been having some minor problems recently. I'm going to be happier sitting down, I think. At any rate, what we could call a specific path loss here, if we take out the gain here, assume it's isotropic, and refer to a reference cross-section of the receiving antenna of 1 square meter, say, we can use this function here as a measure of the detection difficulty. And as you see here, it boils down to just the radar cross-section over the square of the quantity 4 pi r squared. This is the inverse fourth power dependence that everybody is so familiar with in the radar field. I think I went the wrong way there. Okay. This is a plot of the difficulty to achieve echoes from various objects in the solar system. And on the left side, we have the specific path loss that I just described, sigma over 4 pi r squared, quantity squared, in decibels. And here we have a panoply of targets. And I note right away that the moon is off this chart. It's way up here somewhere. And 247 dB to see the moon in terms of the specific path loss. And the nearest planet in terms of accessibility is Venus at closest approach to Earth, where it's about 314. So there's there's a 67 decibel difference between the moon and the next most approachable target in the solar system, namely Venus. That's 5 million times. So that tells you it's a real cliff to climb when you go from the moon out to the nearest object that's out there in space. And that's a really difficult jump, and it's why hams don't talk about doing Venus mounts very often. On the right-hand side here, I've put in the approximate capability of a few of the relatively early research radars that could do a little bit of work in the solar system. And of course, the first one, or one of the first ones, the facility at Goldstone was also in the running in the latter part of the 60s at least. And Millstone weighed in just about capable of seeing Venus. That's the old 440 system, 2.5 megawatts peak power, 150 kilowatts average power, pretty low noise receiver, one of the early Meusers, and it could just about see echoes from Venus at closest approach. And then as time went by and other facilities were developed, Haystack in the early 70s came online with a 3-centimeter system, and it was capable of seeing Venus at the furthest approach when it was behind the sun. It could also see Mercury and Mars, did quite a bit of Mars work. And then, of course, the second Arecibo, the first Arecibo 432 was somewhere in this about 15 dB less capable than the 13-centimeter one is, so somewhere right around in here. And then the 13-centimeter Arecibo, which was upgraded to S-band at 2380, capable roughly down here, and that's roughly where we are today. Arecibo hasn't improved by more than a few dB since that time in the sort of mid-70s. So that you can see what you can see here, that's Venus at close approach, Venus at maximum distance when it's going behind the sun from us. Mars when it's in August when it's closest to us, and this is Mars in early spring or so when it's furthest from us. And then this is Mars at greatest distance. Mercury, again, is in an elliptical orbit, so there are some times when it comes closer to Earth than at others. In June, it's closer than it is in December, just the way the orbits are arranged. Here are a couple of asteroids. Oh, I didn't mention across the bottom is the time delay of the echoes, the round-trip time delay. The moon, of course, is down here in a couple of seconds. Icarus, which came at a close pass to Earth, this is the asteroid Icarus, minor planet in June of '68, and some work was done on it at that time. That was just about a minute round trip. Venus, of course, is something like 5 minutes round trip at closest approach. These are the big gas bag planets, Jupiter and Saturn, which don't have a solid surface, so you can't get an echo from their actual surface because it's just a gas that absorbs the energy incident on it and nothing substantial gets reflected. Now, of course, Saturn's has rings, and those do reflect, as you'll see shortly. That's why they're dotted here. They don't actually give echoes. But the satellites around them can. These are the 4 Galilean satellites around Jupiter: Ganymede, Callisto, Io, and Europa. And all of those have been studied at Arecibo with echoes, as have the rings of Saturn, which are roughly in this general region for detectability as well. More recently, Titan has been studied by Arecibo, though I won't discuss that here. And actually, the tiny moons of Mars can be detected, but other than a bare detection, that's about all you can do. So that's a pretty busy slide, but it gives you a feeling for the relative possibilities one can do with some of these big radar antennas around the world. For some reason, it's not.
Yeah, if you'll just ask me, I'll try to
I'll just ask you, I guess.
Yeah.
Okay, what is the Delay-Doppler mapping technique, this coherent mapping? It basically uses the fact that what we're getting echoes from is a rigid body, a solid body.
Gordon?
Yeah.
Take the pointer.
Okay. So that echoes from it will be coherent for the most part, but because these targets are appearing to rotate as we observe them, there will be a slight Doppler shift imparted across the disk as you see it. In other words, as you can see over here, as the target rotates on its axis, the left-hand side here will be approaching the Earth, the observer, and that will give you a slightly positive Doppler shift. And as you move across the target, the various parts of it will be rotating as constrained in a circular motion around the orbit, around the axis, I should say. And that means that there'll be a slightly lower Doppler shift as you move from this side of the disk to the left-hand side. So that if we can do a Fourier analysis of the echoes as they come back, if we can do them in a narrow enough bandwidth, we can actually isolate echoes coming from disks, from slices, across the visible face of the distant target. This is characterizing a single one of those slices, but they go all the way across. And if at the same time we can resolve the echo in range, then you see we can locate any given measured power density to a specific delay and a specific Doppler, which corresponds to a specific slice on the surface of the target. Now, of course, this is assuming that the target is spherical, and that's a pretty good assumption to first order, not when you really get down to the fine structure, but to first order. So once we do, or if we're capable of doing an analysis, if the echo is strong enough and if it's coherent enough, we can actually map each little element of power that we have at different delays and at different Doppler shifts to a location on the surface of the planet. And notice over here, this is important, that first of all, there's a north-south ambiguity, because as you can see, there's a region up here at a given delay and a given frequency, which is identical to the one down here. So that in order to distinguish those two halves, we have to have another, at least coarse ability to discriminate. If you have an antenna that has a narrow enough beam width, of course you place that beam width up here and you're in good shape, or you can move it down here. At Arecibo, with a 10-minute of arc beam width, even at 432, that's possible because the moon is 30 minutes of arc across. Now on Venus, which is only 1 minute of arc across, that's not possible, at least not easily. So you have to accept the ambiguity unless you're willing to pull some more undertakings, which I'll describe in a minute. But right now, we're talking about doing the moon. And this is the basic principle behind the coherent delay-Doppler mapping. Any questions? Okay, let's move on to the next slide. In 1958, I was working at the Millstone Hill radar, just outside of Boston there in Chelmsford area and Westford area. This was an 84-foot dish designed to see if we could see ICBMs rising up on the horizon at great distances. So it was designed to see 10 square meters at a couple of thousand miles. 2.5 megawatt peak power transmitter. And it had a special tracking horn here so that you could lock on and follow an object as it moved in the sky. But I was able to use this on the side, so to speak, for doing some basic research on lunar echoes. Now this particular dish with a 2.5 megawatt transmitter and a few hundred microsecond pulse width, say, really could get strong echoes from the moon. So signal to noise wasn't a problem on the moon. And we were able to do that. Next slide. This is actually the first delay-Doppler map that, as far as I know, was ever produced. I produced it in 1960, 7 January, I think that is, 1960. And this was just a plot of the echo power in delay and in frequency. This runs from minus 15 hertz to plus 15 hertz. So we're talking about 20 to 30 hertz for the maximum spread here. The resolution was on the order of a few hertz. And then this gives you the delay segment moving back. This is the first echo from the front cap of the moon. And then as you go further back, of course, you're capable of seeing further out and therefore wider and wider Doppler spread until finally you can see the actual limbs of the moon, the full Doppler spread, with the echoes getting pretty weak because, of course, they're coming from glancing incidents. You can also see here, this is the power level that was divided out in order to plot here. So this is basically, these numbers indicate the strength of the echo. You can see it's very strong from the front edge because you're looking at normal incidents. In a backscatter mode, that's where the strong echoes come from. As you move back, you're looking at echoes at an increasing zenith angle for the local portion on the moon, so they get weaker and weaker and weaker as you go back. You can also see another effect here where the echoes are stronger at the limbs than they are in the central regions. And that's because if you remember the, can you go back just 2 slides back? You can see here that there's much more area on the target that's yielding energy that falls within 2 successive range rings and 2 successive Doppler rings out here than there is in the center regions here. So that obviously with more surface area contributing, you get on the average more power out at the edges than you do in the central regions, and you get a lot more power in the front because there you have that front cap being shaved off, and therefore you have this intrinsic ratio of power coming back to the actual map when you put the map on the surface. Now, can you pick up? Okay. Next slide. Here is an example of lunar mapping done some years later, but when the technique was really, really perfected at the Haystack Observatory. We were doing lunar work in the early 70s, the late 60s, early 70s. This just shows you a piece of the lunar crater Alphonsus. This is roughly 100 kilometers across, maybe 80. And the resolution here is down around 1 kilometer. So you can see this picture, which is a radar picture, looks very similar to what you might get with an optical camera with that same resolution. And by the way, that's not very far from the kind of resolution you can get from the surface of the Earth optically with the very best telescopes looking at the moon. 500 or 600 meter resolution, for example. So this is an impact crater on the moon. There's the central peak that was the result of the impact probably several billion years ago. And then the inflow of lava into the crater after it had hit and melted the surface. And then this is the rough region at the edges where the original ejector was thrown out. A very standard form of impact. Next slide. Now moving on to Arecibo in the early 60s when it first came online. This is what it looked like from an aerial photograph. This is the original mesh, the half-inch mesh, basically hardware cloth spread out here over some 30 acres of surface, 1,000 feet in diameter, arranged so that it would be a perfect sphere, at least to within half an inch. We were working, remember, to a 70 centimeter wavelength, so we could tolerate surface errors up to about 2 centimeters, roughly 1 inch. So the surface was pretty good, but it wasn't very good for short wavelength work, but good enough for the wavelengths we planned at that time. This is the elevated structure here. The feed arm here was suspended. This is a line feed designed to make up and correct for the spherical reflection from the surface. I won't go into that further. That's a complicated story in its own right. But basically the feed picks up energy that's coming in from all areas of the feed here, of the reflector, and phasing them up, bringing them into phase so that they reach the top of the feed as a coherent result, and therefore you're getting a coherent signal from basically a capture area of nearly 1,000 feet across. And you can move this for 20 degrees in and out by rotating this feed arm, and by moving this carriage house up across here, you can basically put it anywhere within that region, so you can cover 70 to 90 overhead and anywhere in azimuth. Next slide. Anyway, this shows you again what I was emphasizing a moment ago, that you're getting echoes from the front here, which are strong, echoes from the side, which are stronger than the center, and the weakest echoes of all are coming from this region here, which is this region here. That means that it's a very effective way of measuring the rotation. If you can measure the echo delay strength as well as the Doppler frequency shift strength, you can hit both the radius of the target and the rate at which it's apparently rotating. And the next slide will show we were able to use this to study the rotation of Venus. This is the rotation rate, limb-to-limb Doppler spread effectively, as cycles per second in those days, versus the date. And what happens is that as Venus moves around the sun and Earth moves around the sun, the planet appears to rotate even if it's not rotating, just because of the you might call it the parallax rotation. If you think of objects in an orbit around the sun, and you see that one is moving and the other is moving, just the fact they're in their orbits and you're looking out at them means that they would appear to rotate. So that's an inherent effect, which is then added on top of the inherent rotation of the target. In this case, Venus is rotating in a retrograde rotation. So it's trying to counteract this parallax rotation that we're seeing. And the two add up together. And in fact, as you see, when it's closest to us and the parallax rotation is at its maximum, then this is the minimum in the apparent Doppler spread because the one is counteracting the other. So this was a very precise measurement of what the intrinsic rotation of Venus was. And as you can see, it's a retrograde rotator. Otherwise, this would be a bulge up, not a drip down. And it was 247 days. And by calculating how things worked out here with the known orbits of the planets, you could get the latitude and the longitude of the spin axis of Venus. Next slide. We also applied this to Mercury, which prior to our first observations was always thought to rotate synchronously in its orbit. And if it had been rotating synchronously, this is the limb-to-limb Doppler spread we would have seen on Mercury on that first observation in early 1965. In fact, our observations made it clear that Mercury was not rotating synchronously. When we first observed in this region here around the close approach, the 10th of April 1965, we couldn't distinguish a 59-day rotation rate in the direct sense with a 46-day retrograde sense, which would have given you this curve. But by continuing these observations on for a few weeks, we quickly discovered that it was indeed in a direct motion, but that it had a 59-day rotation, which turns out to be precisely 2/3 of the 88-day synchronous rotation, which means the rate was 3.5 times faster. As you can see in the next slide, this is...
You realize you changed what was in my brain by doing this, because I learned in grade school that Mercury was in a geosynchronous 88.
everybody thought it was.
That's right. And
In
at
1960
high school, you told me I was wrong.
Well, it's interesting because let me just point out why people got trapped into that belief. This is a plan view, if you will, of Mercury in its orbit around the Sun. And the little arrow here shows you how it's pointing, assuming it's rotating on its axis every 59 days. Well, because Mercury is in an eccentric orbit, it moves more rapidly in the part of its orbit when it's closest to the Sun. It also is closer to the Sun, so its motion around here is forcing the direction of the Sun to rotate more rapidly than it would out here, even if the velocities were the same, but in fact it's faster. So this effect really speeds up the apparent direction. And a 59-day rate, turns out, tracks the Sun very closely as it goes through its perihelion, the close approach to the Sun. And then, of course, as it slows down up here, Mercury still is rotating at the same inherent rate, 59 days, so it starts moving away from pointing towards the Sun. And as you get out here, you can see it's pointing off there, pointing off here, pointing off here. By the time it gets back after 88 days to its original position here, it's pointing 180 away from where it was before. Well, of course, there's several factors at work here, but the first thing you notice that the Sun, of course, raises tides on Mercury. Even though it's a solid object, there are tides. There's dissipation that takes place. Mercury is losing rotational energy as it passes through perihelion at a much greater rate than it is at any other part of its orbit because it gets further from the Sun. That tidal torque is very much less. And in a sense, you might think, as a scientist, why didn't somebody realize that in the beginning? That the Sun was going to try to torque and capture Mercury at a time when that loss is very high, and it's going to be much more likely to trap it in a 3/2 spin rate than it is in a 1-to-1 spin rate, because this is where Mercury is not rotating with respect to the local tidal force. And in retrospect, it seems so clear, but it's a good example of how people can get trapped in a mindset and not think in a wider set. And I came into this without basically having had that exposure as to why it had to be 88 days, so it didn't seem to me that difficult to accept it was 59 days. At any rate, that was, I have to say, brought me onto the astronomical scene, and was an interesting time. Next slide. Now, getting back to mapping planets, as I said earlier, you need to distinguish between these two points of ambiguity, which you're faced with if you're using Delay-Doppler techniques. And if you can't resolve that echo on the planet by the size of your antenna response, which you cannot do on a target like Venus, which is at best a minute of arc across. Then the thing to do is to bring in an interferometer. And Sam Harris had built a reflector a few miles away, which he wanted to do moon mounts with, of course, that being his shtick. But we were able to talk him into letting us use it as an interferometer with the basic receiver at Arecibo in a coherent arrangement. Here you see the Arecibo, here's the auxiliary antenna, and if you can maintain a reference signal between them, you can then combine the echoes you receive at these two coherently, and because they're some distance apart, 6 or 7 kilometers apart, you will now be able to form fringes in the usual interferometer sense, and this is the response that you might get from a system like that, which you can arrange to put a null on one while you're putting very nearly a maximum on the other, and that way you can separate them. Now, of course, you have to be clever about this because you're mapping a large region of the planet, so that you've got to arrange the observations so that you can manage to put a null on one. That's easy enough. You just change the relative phase arbitrarily till you do that. Now, if both of these points fell on a minimum here, you'd be in trouble. But fortunately, as the target moves in the sky, the projection of the baseline, which is fixed to the Earth, changes, so that the spacing of the interferometer fringes ever so slightly changes over the course of a 2 or 3 hour mapping period. And so what you can do in the beginning might be up here, and then in the end you might be able to do down here, and you just have to sew up all these echoes together in order to, over a 3 hour interval, in order to resolve this ambiguity. But as I think the next slide shows you, this that's a picture of Sam Harris's little Arecibo. It was in another little sinkhole about 7 kilometers away from the main Arecibo antenna. And it was only 100 feet, so it wasn't anywhere near as strong as the echoes from 1,000 feet Arecibo, but nevertheless were quite capable of being used in this as an interferometer, being used to do the separation of echoes from those 2 points of ambiguity. And I think the next slide is, this is a radar map showing some of the better results that were obtained using Arecibo. Actually, this is using it as a 13 centimeter system in around 1975. And really, you have here something like 3 or 4 kilometer resolution. This is the view of the disk of Venus that's seen during inferior conjunction. Venus is in a semi-locked rotation rate, in a sense, like the moon is, so that at close approach, when you can map this readily, it's always showing you the same face. So you can't see the backside of Arecibo, of Venus, from Arecibo or any other earthbound site readily, because by the time it's rotated more around there, it's too far away, it's too weak. But here you can see some of the major features. This is the Lakshmi Planum area, which is an elevated region, very smooth, a lava flow. These are mountain ranges around it. This is the very high Maxwell Montes region, which is up about 15, it's about 10 kilometers above the main surface here. And it has a very reflective surface. We don't yet know quite why, but it's some kind of a mineral that's been deposited on the surface that's conductive in some way, so that it gives you very strong echoes as compared to echoes from the rest of Venus. The Beta Regio region, this is another set of volcanic peaks in this region. And then you can see all kinds of little fissures here, which are the result of local roughnesses. I can't go into the details on the surface, but this really was a very interesting map. There are some impact craters you can see here quite well. And it really wasn't until 1990, when we went there with the Venus radar mapper, that we're able to get higher resolution and, of course, the entire planet. Next slide. Oh, this is an example taken from recent work, well, recent 1990s, by John Harmon down at Arecibo, which was very fascinating work. This was looking at Delay-Doppler mapping of Mars. Sorry, Mercury. What am I saying? Mercury. And you can see here the polar regions mapped out from the radar, and down here the optical observations made from Mariner 10 spacecraft. And if you do a careful comparison, you can see that the really bright, round, scattering objects here are related to craters as seen in the optical images, but you don't see the brightness from any crater that is exposed to the sun. Mercury is tilted in such a way that there are regions near its poles where the sun never shines. In other words, it's blocked by the crater rims. And obviously those regions can get very cold because they're exposed to space, but they never see sunlight. And there's no atmosphere on Mercury to speak of, so that there's no way of carrying heat in. So ice can form there and remain over the age of the solar system. Very nearly, you're talking about something like 50, 60 degrees Kelvin for the effective temperature of the bottoms of these craters. Same thing at the south pole of Mercury. Again, you can see this large crater here. Here is what appears to be water ice. We think it's water ice because water ice is the only known substance that is sufficiently lossless at these cold temperatures to allow radar energy incident on it to be scattered around inside and then come out again in the back direction. And that's been tested by observations on Saturn's rings, for example, which are ice, and on Galilean satellites. Next slide. This is Saturn as seen optically. Here's the gas bag planet. These are the rings. And then the next slide is a case of observing echoes from the rings. We can't see echoes from the disk itself, but because the rings are made up of chunks of ice, anywhere from a few centimeters in size up to maybe tens of meters in size, and they're cold ice, these are very effective backscatter to microwave energy. And in fact, very strong echoes at Arecibo, and they've been also seen at Goldstone and other sites. This shows you the situation you have. The rings, of course, are not a rigid body in rotation. They're little blocks of ice, each one in its own Keplerian orbit. So the part of the rings that are closer to Saturn are moving more rapidly, and as you move away out here, they're moving less rapidly. And then, of course, you have the projection of that motion in the Earth's direction here taken into account. So that means that it's a very different sort of map. It wasn't like that bullseye diagram I showed you for a rigidly rotating object, but rather these are objects moving in Keplerian orbits, so that if you do map the location at a given Doppler shift, these are the sort of iso-Doppler shift contours that you will see. So that when you do a delay-Doppler analysis, you bite off the front of the rings here, and you don't get a very wide spread in frequency because you're not seeing out to the high regions here where they're moving directly away from you or towards you. It's symmetric, so I'm only showing you half here, but here is the actual data we got. As you move in, you begin to get echoes at ever wider Doppler shifts, and you don't get echoes at low Doppler shifts because there's nothing there at that range to reflect at that Doppler shift. And then as you move further back, you start to basically return to this mode, except now in the back region, the planet is shadowing. So you don't get this region filled in as much. So you begin to revert to this, but you never do get all the way back because this chunk on the front is just never visible to you because it's blocked by the planet. This is a plot of the integrated echo as a function of distance reflected out into the ring structure, and it compares the radar energy that's seen. That's these barred results here, the black dots with the bars, and I'm sorry, the dots are the optical, whereas the bars here are the radar results. And you can see that there's some terms of agreement. The D ring here is showing up in optical as the weakest ring, the C ring, and then you're into the A and B rings, which are the rings that really shout at you optically, and they're the rings that really shout at you in radar. So it's very interesting to see there isn't a perfect agreement, but there's a pretty good agreement. At any rate, one more. Yeah.
The rings appear at different inclinations over the years. Does that give you more information?
And that does make a difference. This is how they appeared in 1973. Yes, you're absolutely right. What have I left out? Well, there are ways of using even further finely refined interferometers to measure the height. You've dropped the assumption that it's a sphere now. You've got X and Z from the delay and the Doppler. You need Y, the third Cartesian coordinate. You get that from an interferometer. So you can actually map things like the moon and to some extent the surface of Venus if you have a very much finer interferometer at your behest. And I can't get into that, but that was done very successfully. We were able to map the topography of the moon. Asteroids and comets in the last 10 or 15 years are really now the main focus of radar astronomy because of the interest in them as potential Earth impactors. I can't get into that, but that's another big field. And of course, not even mentioned here is the coherent Doppler, range Doppler mapping that spacecraft do when they actually go out to the planet, go and orbit around it, and look down and do what's called synthetic aperture mapping, the things the military do when they're trying to look into areas they aren't allowed to fly over. They can look in and do some pretty decent mapping there. So those are all related in a sense to this technique. But I've tried to give you a little bit of a feeling here today, and I know it's hard to do that in a short talk because there is a fair amount of mathematical transformation and so forth that has to be done. But I'm hoping that gives you a feeling for it anyway. That's the end.
Germany Hotel Radio, Germany Hotel Radio, USA, Kilo Papa 4 Alphonsus.